Imagine you have a special pair of socks. One is bright red, the other is deep blue. They are identical in every other way. You place each sock into its own sealed box. You shuffle the boxes so you don't know which is which. Then you give one box to a friend. Your friend boards a spaceship. The ship heads to Proxima Centauri, 4 light-years away. You wait patiently on Earth. The moment you open your box and see a red sock, you instantly know the other box must contain the blue sock. No mystery, simple logic. The outcomes were predetermined when you packed the boxes. But now, step into the quantum world, a realm far stranger than our everyday experience. Imagine those aren't socks, but tiny particles. These particles don't have a definite color until you look. Before you open the box, the particle isn't red or blue. It exists in a haze of possibilities, a ghostly state of being both red and blue at once. This isn't just missing information. It's a fundamental property of the universe at tiny scales. The act of observing, opening the box and measuring, forces the particle to choose a state. It snaps out of fuzzy potential into one definite outcome. So, what exactly is quantum entanglement? At its core, it's a special connection that can exist between two or more quantum particles' electrons, photons of light. When particles become entangled, they essentially lose their individual identities and behave as a single, unified system. Think of them not as two separate entities but as two parts of one whole, no matter how far apart they are. What happens to one particle directly and instantly affects the other. This isn't a case of one particle sending a message to the other. It's as if the universe itself doesn't consider them separate things to begin with. Their destinies are intertwined. To create entanglement, you typically need to generate particles from a single source or event. For instance, some crystals can take a single high-energy photon and split it into 2 lower-energy photons. These 2 new photons are born together, and their properties are linked from that moment of creation. If you set up the experiment so their spins must be opposite, they will be. But here's the quantum twist. Neither photon has a definite spin until it's measured. One might be spin up and the other spin down, but until you look, they are both in a superposition of up and down. The moment you measure one and find its spin up, the other instantly becomes spin down. The unified system is described by a single mathematical object called a shared wave function. Our daily lives are governed by what physicists call classical mechanics, throwing a baseball, driving a car, watching planets orbit the sun. In this classical world, objects have definite properties. If you know everything about the ball now, you can, in principle, predict its entire trajectory. Information is local. To affect the ball, you have to touch it. The quantum world, however, plays by a completely different set of rules. Down at the scale of atoms and particles, certainty dissolves into probability. A particle like an electron doesn't have a definite position until you measure it. Superposition, spinning clockwise, spinning counterclockwise, existing in multiple places simultaneously. Observation forces a choice, collapse of the wave function. Classical system analogy, 2 socks in boxes, correlation from pre-existing information. Blue sock was always blue, red sock was always red. In an entangled quantum system, properties are not predetermined. Particles are in an indefinite state. Their correlated outcomes are created on the fly at measurement. Crucial difference. Classical correlation, discovering hidden information. Quantum correlation, creating information from pure potentiality. Clash, local, deterministic classical world versus non-local, probabilistic quantum world. Entanglement is revolutionary. It breaks the classical rule of only local influence. The discovery of quantum mechanics in the early 20th century sparked one of the most famous scientific debates in history. On one side was Niels Bohr. He argued that the fuzzy, probabilistic nature of the quantum world was fundamental. On the other side was Albert Einstein, who could not accept the core tenets of quantum mechanics. He famously stated, "God does not play dice." He believed quantum randomness signaled an incomplete theory. There must be hidden variables, local, underlying properties that determine outcomes in advance. Einstein, Podolsky, and Rosen devised a thought experiment, the EPR paradox, to argue quantum mechanics was incomplete. Erwin Schrödinger proposed his famous cat thought experiment. A sealed box contains a radioactive atom, a Geiger counter, a vial of poison, and a cat. If the atom decays, the cat dies. Until the box is opened, the atom is in a superposition of decayed and not decayed. And so the cat is, disturbingly, both dead and alive in the thought experiment. This paradox highlighted the strangeness of applying quantum rules to macroscopic objects and the puzzle of where the quantum ends and the classical begins. It forced physicists to confront uncomfortable questions about measurement, reality, and the observer. It was a brilliant challenge that pushed quantum foundations toward testable ideas. To get a better handle, let's use a simpler analogy, a pair of magical spinning coins. Imagine a machine that produces 2 coins at a time, guaranteed to land on opposite faces. While spinning, their outcomes are undecided. A good picture for superposition. We both take one, travel apart, and reveal simultaneously. A pair of magical spinning coins, minted together and guaranteed to land opposite. While they are spinning, their outcome is completely undecided. Not heads or tails. They exist in a spinning blur of pure potential, an analogy to quantum superposition. You catch each coin in a cup. Give one to a friend who travels far away. You both agree to slam your cups down and reveal at the exact same time. You lift your cup, heads. Instantly you know the distant coin is tails. Einstein would argue the coins had hidden marks, secret instructions etched at creation. Bohr and quantum proponents argue there are no such scratches. The coins truly have no definite state until measured. The system only knows one thing: the outcomes must be opposite. Individual outcomes are not predetermined. When you measure your coin and see heads, reality randomly picked that outcome, and the entangled system updated instantly to ensure the other is tails. The correlation is real, but the individual outcomes are not predetermined. This lack of hidden instructions is what makes quantum entanglement fundamentally different from any classical analogy we can devise. In the 1960s, John Bell devised a theorem that turned the debate into a testable prediction. He showed that if hidden variables were real, correlations would be limited by a mathematical bound. Bell's theorem proposed a game that nature had to play, and it was experimentally testable. The first crucial experiments began in the 1970s and early 1980s, most famously by Alain Aspect and colleagues. They generated entangled photon pairs and sent them to separate detectors. A central source emitted photons to 2 distant detectors with adjustable settings. By randomly changing detector settings at the last moment, they ensured no signal could coordinate outcomes. Fast timing created space-like separation. Measurements could not causally influence each other at light speed. The results were unambiguous. The experiments violated Bell's inequality. Over and over, correlations exceeded Bell's bound. No local hidden variable model could explain them. Subsequent experiments closed loopholes and extended tests across hundreds of kilometers and between satellites and ground stations. Einstein's discomfort was understandable, but nature spoke clearly: entanglement is real. Today experiments are ever more precise, closing every conceivable loophole. Entanglement has been demonstrated over hundreds of kilometers and between ground stations and satellites. Nature at its deepest level is non-local, and that fact reshaped physics. The instantaneous connection of entanglement naturally raises a tantalizing question. Can we use it to send messages faster than light? Imagine you and a friend on Mars share an entangled pair. You agree spin up means yes and spin down means no. For many years, entanglement was a philosophical curiosity. Today it's the backbone of emerging technology. Scientists and engineers are harnessing spooky action to build revolutionary devices. One of the most promising fields is quantum computing, which could solve problems classical computers cannot. Classical bits are 0 or 1, a qubit can be 0, 1, or both at the same time. Entangling multiple qubits creates a massively powerful computational space. A few hundred entangled qubits can explore more possibilities than there are atoms in the universe. This could revolutionize drug discovery, materials science, and financial modeling. Entanglement also enables ultra-secure communication, quantum key distribution, and quantum networks. If an eavesdropper measures entangled photons, the disturbance is immediately detectable. Alice and Bob see the disturbance and know their key is compromised, guaranteed by physics. Experiments have teleported quantum states from lab to lab and even to satellites, foundations of a global quantum network. Entanglement has been demonstrated with photons, electrons, atoms, and even tiny vibrating diamonds. The spooky action at a distance is being tamed and put to work, building the tools of the 21st century. The discovery and confirmation of quantum entanglement does more than promise technologies. It alters our perception of reality. It forces us to abandon the comfortable picture of a world made of separate, independent objects. Instead, the universe appears profoundly interconnected, a holistic web where here and there blur. The fate of a particle here can be intrinsically tied to another in a distant galaxy, not via force but shared, non-local existence. This has deep philosophical implications. It challenges the idea of empty space separating things. Maybe our three-dimensional space is emergent, a surface over a deeper connected reality. Underneath, a network of connections may be doing the real work of the universe. The particles and their connections are not just on the stage, they are the stage. We are not just observers of this cosmic dance, we are part of its interconnected fabric. From a perplexing thought experiment to a proven feature of our universe, this journey is a testament to human curiosity. A bold idea is proposed, debated, an experiment devised, and nature gives its verdict. Nature's verdict was more wondrous than anticipated. We should be cautious about projecting everyday intuition onto the cosmos. The mind-bending truth of entanglement is an invitation to keep questioning, exploring, and remaining in a state of wonder. What other hidden connections does the universe hold? The next chapter is waiting to be written. To send a yes, couldn't you force your particle to be spin up and thereby force theirs to be spin down? The core issue is randomness. You cannot control the outcome of your own measurement. It is fundamentally probabilistic. When you measure, you have a 50-50 chance of up or down. You can't force one outcome to encode a message. From Mars, the results also appear random. Your friend cannot tell whether a given result was correlated with you. Only by coming together later, or communicating classically, can you compare lists and see the spooky correlation. Then you see the perfect anti-correlation. Every time you got up, they got down, and vice versa. Entanglement is instantaneous, but the information is hidden in random noise. You can't reliably encode messages. This is formalized in the no communication theorem. Entanglement cannot transmit usable information faster than light. You can't use entanglement to warn Earth of an approaching asteroid faster than a light-speed signal. The cosmic telephone is there, but you can't choose what to say with it. Causality and Einstein's speed limit remain intact. Entanglement doesn't break causal order for information transfer. But entanglement is not useless. It's a resource that enables teleportation, secure keys, and quantum computation. Let's explore the future.